and how to ensure shared accountability. And this is work that is with myself and Mike Bioki, who is in epidemiology and population health at Stanford. So just a quick introduction to me. My name is Jordan Radu. I'm on the faculty of statistics at the University of Virginia. I work at the intersection of machine learning and statistics. I specialize in methods for high-dimensional time series and also data visualization. I work in a variety of areas: text analysis is how I know Tommy, neuroscience, and sports science. And if you want to reach me, you can email me. I'm happy to receive emails, jordan.radu@virginia.edu. So what I want to talk about today is, like I said, let me just show you this screen. This is a paper that we have on arXiv, which sort of forms the basis of this talk. So if you're interested in some of the details, feel free to check it out. And of course, you can email me and I can send you the link. But I want to talk about, how we share accountability as data scientists. We're in a really exciting time to be a data scientist because there's an explosion of interest in using data to make decisions, and an explosion of algorithms that can help with that can help us do that. And they're very powerful algorithms. But inevitably these algorithms are going to fail. And the question is, how do we protect ourselves from being the ones that are responsible? Because we're the data literate ones, in the room. And how do we make sure that we're not the only ones who are responsible for the failure of an algorithm? And so I looked up, to start out, I said, let me get a good definition of accountability. And from the Oxford English Dictionary, the definition is the fact or condition of being accountable, which I always feel like there's some British person that gets 50 pence every time I look up a definition that references itself. So they got me there. So I decided to look up what accountable was. And it's required or expected to justify actions or decisions. So this is what we're going to talk about today, is how can we justify our action or decisions when it comes to especially machine learning algorithms, which are of course very popular today and a big part of what we do as data scientists. So to whom or what are we accountable? And the main idea is that involved in these algorithms and deploying these algorithms are stakeholders. And we typically divide these into multiple groups of stakeholders. And I'm mostly going to think about two different groups. One is the primary stakeholder. These are the decision makers. These are the people that hire you. These are your colleagues, maybe, or these are folks for whom the decision to actually use an algorithm or try to be data-driven, it rests on their shoulders. So these are like your C-suite at a company, shareholders, maybe a specific department like marketing department, a scientist who's interested in using, really leveraging data, something like maybe a governmental organization, the Bureau of Labor Statistics, for instance. You are a primary stakeholder as the person who is designing or coming up with these algorithms, et cetera. So those are our primary stakeholders. And this is really the group that we want to share accountability with. We want to make sure that when we deploy an algorithm, if that algorithm were to fail, that this whole group, the C-suite or the marketing department, has a stake in that algorithm, has some accountability for the fact that it's being used. The secondary stakeholders are the folks who are impacted by the algorithm, but they're not responsible for the decision to deploy the algorithm. So these are users of technology. These are patients at a hospital. These are citizens who are, who are impacted by a policy decision in the government, et cetera. So these are folks who might be harmed by our algorithm and who are expecting accountability. And again, we want to try and share that accountability with the primary stakeholders. So how do we actually share accountability? Well, I'm going to loosely talk about two different groups of algorithms. One is sort of statistical models or algorithms, and one is machine learning. That's not a great breakdown. It's kind of a colloquial breakdown. I'm going to offer a better breakdown later, but I just, I'm not trying to make a value judgment here between the two, but this is kind of a first pass at breaking down these two, types of algorithms. So with statistical algorithms, what I'm at least for now calling statistical algorithms, we can map our models onto domain knowledge or beliefs. So we have the ability to interpret these models in the context of the science or the social science in which these models are being placed. We also have a good mathematical understanding of the assumptions in our model, so we can communicate those assumptions to our stakeholders and talk about what happens when these assumptions are not met. And we also can make, probabilistic statements about the success of our model and how often it may fail, things like that. So these are very mathematically driven models that can be mapped onto domain knowledge. So, something like a regression is a good one to think about, where we can map coefficients onto domain knowledge, right? When there's an increase in some variable, our output increases by so much, right? And that's something that we can latch on to as, or a scientist can latch on to, or someone in marketing, for instance. So that's how we would share accountability with a statistical model. We would get everyone to buy into our model, that our model represents their current beliefs about our system. But how do we do that with machine learning? It becomes much more challenging, because in machine learning, algorithms can be large, they can be complex, they can be difficult or impossible to map onto domain knowledge. Even in like a very simple machine learning algorithm, we can start to run into these difficulties. And so the success of an algorithm is really a complex interaction between the algorithm itself and the sort of idiosyncrasies of the data that we use to train those algorithms. And oftentimes it's the case that an algorithm works really beautifully on one data set, and then we try it on a new data set, which we think essentially has the same characteristics, and then it fails, and we have no idea why. So this kind of is concerning, right? Because we think that, well, what happens if we deploy our algorithm and it all of a sudden fails and we can't figure out why? So the issue here that I'm trying to set up is that sharing accountability now becomes a very difficult thing to do, because we ourselves don't fully understand these algorithms. How do we expect someone who's not data literate, who doesn't have the technical skills, to also share in the accountability? I will say that it's even hard when it comes to statistical models, right? I speak with, domain experts all the time. They're brilliant people. They may be in a domain that is leveraging data, but it's still, there's a disconnect in terms of trying to explain to them sort of the ins and outs of statistical modeling. And so, that task just becomes, multiplied when we think about machine learning. And these kinds of concerns have actually been raised for quite some time. So on the left here, we have Ali Rahimi, who in December of 2017 kind of shook up the community that's now known as NeurIPS by making the statement that machine learning is alchemy, that we don't know, we don't understand our algorithms. They're doing amazingly powerful things, but we have no idea why they're working. We really are kind of going off of heuristics. And so this was a big concern. And, he got into somewhat of a debate with Jan LeCun. And actually, if I don't know if there's a way to share the slides, but those links are to articles that talk about this debate. But Jan LeCun had a response that basically said, yeah, okay, we don't know the mathematics. The mathematics is always runs centuries behind our engineering, but we're doing amazing things. We shouldn't slow down just because we don't really understand these models. And you can see both sides of it, right? We're doing exciting things with these machine learning algorithms on the one hand, which is really great. On the other hand, they fail, and they can fail in actually quite dramatic ways. What I kind of perceived happened in the community at that time was there was really a division between people who got really nervous about using algorithms and people who got really excited about it and sort of kept on driving forward. And at the time I was thinking to myself, there must be some middle ground. There must be some way to leverage machine learning while also acknowledging that it could fail and trying to mitigate the potential downsides. I think Jan LeCun raised some interesting points, but one thing that he wasn't really acknowledging is that we're not living in an academic vacuum. These algorithms are being deployed, they are being used on real people, and have real consequences. So if you Google something like machine learning fails or something related to, or maybe your favorite domain, machine learning fails, there are numerous articles on this, right? Whole entire businesses that fail, algorithms that, or algorithms that a company deployed that failed. It's not hard to find examples of this. This has led to things like death, certainly inequity, biases that are being encoded in our algorithms that we want to try and avoid. Injury, poor health outcomes have been linked to sort of machine learning failure. Emotional trauma. It's not getting better. Actually, speaking of emotional trauma, if you remember in, I think, 2015, 2016, Google had an image recognition algorithm that mislabeled a Black person, and it really kind of caused a huge controversy over their use of machine learning. And their response was to, stop labeling with the harmful label. And you may say, okay, that was a while ago, things are improving, it's going to get better. But actually, Facebook just committed the same sort of transgression about a month ago with their image recognition algorithm. So, despite having much better data, much more sophisticated algorithms, the problem's not going away, and we can't guarantee that the problem's going to go away. There's actually an incident database for AI algorithms that fail. It's not hugely populated right now, but the fact that it exists kind of suggests that people are concerned about the rate of failure of these algorithms and approaches. And Andrew Ng, who is a prominent person in AI or ML, came out recently and actually has been sounding several warning bells, but saying not too long ago this year that we still haven't figured out AI in healthcare. We can spin up algorithms that predict really well on an in-house data set, say at Stanford where he is, but you take it down the road to the hospital down the road, and it just fails again. That's a big concern. And I'm not bringing these things up to try and say that we shouldn't be doing ML. I don't think that at all. I think that ML is incredibly powerful, and we should use it where we can. But again, I come back to this worry that as data scientists, we're the ones who sort of okay the use of an algorithm. And these algorithms are so, are often black boxes. They're complex to the point where I don't think we have a chance at really, having our non-technical stakeholders really buy in to an algorithm in the same way that they will in a statistical model. So what I'm going to try and do today is talk about how we can get sort of stakeholder buy-in so that the stakeholders also share that accountability in case something does go wrong. Okay, so to return to the definition of accountable, the idea here is that we're required or expected to justify our actions or decisions. So let's take a step back, go back to basics and ask ourselves, how do we actually justify to ourselves as the data scientist that this algorithm is the algorithm that we want to use, okay? The answer is simple, although I'm kind of waving my hands here at a lot of details that aren't so simple. But the relative framework of how we do this is pretty simple. We grab a data set, whichever data set maybe the company has that they want us to use, or we create our own data set. It's a labeled data set. We code up some algorithms, some competing algorithms that we're interested in using, and then we see which one does best. Right? And again, I'm waving my hands at a lot of details because I want to abstract out this idea here. But for the most part, this is the basic framework for how we go about deciding, okay, I want to use this algorithm in this prediction problem. We kind of just see which one does best. And it turns out that that's a really powerful form of reasoning. And one thing that Mike and I do in our papers, we name this form of reasoning, which we haven't seen done before, but we call this outcome reasoning. And it's distinct from model-based reasoning, right? When we think about statistical models, we really think about going through and understanding how our model maps onto a domain. Does it make sense that this coefficient is set the way it does? We look at things like our confidence in coefficients. Does it make sense that this coefficient is is not bounded away from zero, whatever it is that we do. That's kind of a model-based reasoning. We really think about how our model maps onto the domain. And by this, I actually mean the domain of our data, the covariates in our data. How does this model map onto those covariates? Or do our covariates sort of map onto our knowledge of that domain? With machine learning, it's different. We look to see, are we getting the right answer or not? And it turns out that, like I said, this is a really incredibly powerful form of reasoning. It's allowed for the rapid development and assessment of algorithms. You don't have to put in the hard work of, is this mathematically justifiable? Am I violating any assumptions that my algorithm is making about the data that that I need to be aware of? We can dispense with all of that. We simply say, with suitable protections, right, with cross-validation, et cetera, we simply say, is this algorithm making good decisions on the data that I have? Is it actually getting things right more often than another algorithm? That's how we sort of compare two different algorithms to make a decision about which one we want to deploy. So like I said, it's really moved our consideration away from the input space. What's our covariates? How's our algorithm handling those covariates? How does that map onto our understanding of that domain and our understanding of the science behind that? It removes us from that sort of set of considerations to how is it doing on the outcome? Are we getting predictions right? Are we getting predictions right enough of the time? If this is a sort of a regression, are we close enough? Are we getting close enough to where we want to be? That's a really easy thing to understand, right? You give me a metric and I can understand. I don't care how complicated your algorithm is. I can understand how your predictions and the ground truth interact, right? According to the metric that you gave me as the metric of interest. This is incredibly powerful. It really removes the burden of algorithmic assessment. And it turns out, sorry if you can hear my baby in that background, it turns out, just adds a little pizzazz to the talk. It turns out that outcome reasoning is actually the intellectual engine of probably the most important framework that we have for machine learning algorithmic development. Okay, so I'm going to actually unpack that. I'm going to talk about what that framework is. It's actually something that you all will clearly recognize, although might not have recognized it formally before. But it turns out that outcome reasoning is the intellectual engine for this framework. And I'm going to convince you, I hope today, that this framework is why machine learning is where it is today. So the framework is called the Common Task Framework. And like I said, I would almost say most or even all of the rapid success in prediction has come from this innovative infrastructure. Okay, it's really what's gotten us to where we are today when it comes to machine learning. So what is the Common Task Framework? Well, you start with a curated data set. This data set is widely available or available to everyone who it needs to be available to. There's a task that's clearly described, right? I'm going to give you a set of X and I want you to predict Y. There's a metric that tells us how we're going to measure our success. And then there's a data set that we've held out that's going to be reserved for evaluating performance. Okay, this is the Common Task Framework. I'll give you an example of the Common Task Framework, the Netflix competition. That was a Common Task Framework competition that if you're familiar with the Netflix competition, you can see all the parts of this Common Task Framework in that competition. If you've ever looked at Kaggle and participated in one of their competitions, Kaggle is a wonderful example of a Common Task Framework. They give you a data set, they tell you explicitly what they want you to do. They say, this is how we're going to evaluate. And then you go off with your data set and try and spin up a nice algorithm. And then you submit your algorithm. They compare it to their data set that you don't get to see. And the winner is announced, right? Now there are relaxations to the Common Task Framework. So let me actually go into the history of the Common Task Framework, and I'll talk about some of the relaxations that we see today. So a lot of this comes from discussions with Mark Liberman, who's at the University of Pennsylvania. So the Common Task Framework, the formal framework, actually traces back more or less to DARPA in the 1980s. I think 1986 might have been the first competition that they ran. The idea of the Common Task Framework were all those components that I talked about, the data set, the metric, the tasks, they were very heavily debated. So it wasn't just like an accidental thing like, oh, here's a data set, let's all work on this. It was, a community got together and really tried to understand what do they want out of this framework. And so what's the best data set? What's the best metric to put forward in order to get what they want? An organization, NIST, actually curated the data. They were the kind of responsible for officially setting the task. They maintained the test data, so that was firewalled from researchers. Researchers would send NIST their code and say, here you go, here's my algorithm. I hope to do well. And every year a conference was held. The winners were announced, and then everyone would kind of share insights like, okay, what'd you do? What'd you try? How did you overcome these issues? And in that way, progress was measurable, right? Every year we're getting better and better and better at these kind of tasks that are set forth. The methods had to be shared because otherwise NIST wouldn't be able to run your algorithm on their data. And so there was really a community that sort of built around a culture that was built around this Common Task Framework. The task itself changed pretty often, almost yearly. So it wasn't, tasks that go on for 20 years. These things were really changing essentially every year, what exactly they wanted you to do with the data. New data sets, new goals, every year these changed. The metrics, the way we evaluated how an algorithm did, they didn't change as frequently, but again, they were always discussed. Is this the right metric that we want to be using? And how did they decide what task or metric to use? Well, they were really set to overcome technical challenges. They weren't set to be deployed. Nothing was meant to be deployed here. This was back in the day when we were decades away from deploying any of these algorithms. They were really meant to overcome technical challenges that we were having in many different domains. And this typically was applied to human language technologies. But the idea was that let's set a task, let's set a metric so that if we can improve in that task and in that metric, that will improve a little bit in all of these domains. We'll kind of inch forward in our ability to sort of make algorithmic decisions in all of these different domains. And again, any kind of actual deployment was decades away. We didn't worry about actual, and I'm saying we, I'm obviously not, hopefully you could tell I'm not old enough to have been a part of that. But, we're really not worried about this actually being used on your iPhone or anything like that. This was something that was, not even envisioned how we'd actually use these in real life. These were just set to overcome sort of technical, sort of almost academic challenges, but things that eventually would help us deploy once we got to that point. So again, all we want to do is sort of inch forward in the right direction. So a couple of interesting things about this framework. It started out as kind of people hated it. They didn't want to be told what to do. This was sort of geared, aimed at the academic community who was used to sort of setting their own agenda. They really disliked the fact that, someone comes in and says, here's your task, here's your data, here's your metric, go. But innovation was incredibly rapid, right? They were, they were finding that every year they were making these huge strides because of this setup of this competition. And especially that was compared to what was happening in the 60s and 70s, where someone would come out and say, oh, I've got this wonderful algorithm, it does really well. And you would take it, you would apply it to your own data, and it really failed. And so it was all these kind of one-offs, like people coming out and saying they had a good algorithm, and maybe they did for their own data, but it wasn't really applicable anywhere else. And that was kind of problematic. That the community didn't feel like there was really any progress that was being made at the time. And all of a sudden they're in this sort of framework where, again, year after year, they were making huge strides, clearly measurable success. They could tell, they could measure the fact that they were getting better and better. And all of a sudden a culture developed around this. And it became so popular that researchers actually were joining up. But actually, I don't think I mentioned this. They were paying researchers to join this competition, because they couldn't get researchers just join for free at first. They were paying them. They're saying, we'll pay you to like spend time on this. And all of a sudden they were like looking around, they're like, wait, we're not paying a lot of these people, but they're still here. And that's because that's where the success was. That's where the innovation was. So everyone's really excited to be a part of it. And it became a part of the culture, right? To work on these common tasks. There were a couple shifts in the 2000s. So one big shift is that funding changed from the government to industry. And this happened in academia at large, not just in sort of this common task framework, but really you see a shift in who's funding work. It used to be, I saw a chart once, I wish I remember the source of it, but where government dominated funding. And so they were really setting the agendas. This is back in the 60s, 70s, 80s, 90s. And then it tanks in the 2000s. All of a sudden you have your Googles, your Facebooks kind of crop up, Twitters, whatever that, where now all of a sudden they were pouring money into academic research, and government was being dwarfed. The contributions for government were being dwarfed by industry. And so that really changed the focus and who was setting the agendas. But you also saw all of a sudden technologies were getting really close to deployment. And that was a major shift, because again, earlier when they were really thinking about how to set the agenda, how to set the tasks, the data sets, et cetera, deployment wasn't an issue, right? They weren't worried about, well, is this technology going to fare well in deployment or not? That wasn't part of the package. All of a sudden, Google was deploying these technologies. Netflix was deploying these technologies. So the sort of the stakes of the game had changed a little bit. And that really changed the way that the CTF moved forward. So we see now like that there's kind of relaxation of the CTF. I will say that, again, there were still very much CTFs that existed. So Netflix was really close to a CTF. I mean, they relaxed in the sense that they let you see the holdout data set more than once. Okay, that's a relaxation from the original CTF. Kaggle, I'm not super familiar with Kaggle. I believe that they also, maybe depending on the competition, allow you to query the test data set more than once. That's, again, a kind of a relaxation. But, more or less, we still see these, fairly robust CTF-like competitions out there. DARPA does still hold true CTFs, so that they are still pushing forward with this formal framework, especially inside the research communities. But one nice thing about Kaggle and Netflix is it's really opened up competitions to anyone, not just inside of academia, which is quite nice. But also, I would argue that we run CTFs as data scientists, right? We're kind of trying to pick, we're trying to train up an algorithm or pick an algorithm or maybe modify algorithms to sort of suit our purposes. What do? We have a sort of a data set that we want to test this out on. We want to build our algorithm on. We sort of reserve a test set that we don't want to look at too often. And we sort of try algorithms and we tweak them and we try them and we sort of have a competition. We call it often a bake-off nowadays, a bake-off between our different algorithms to see which ones are going to perform the best. So in a way, that's a CTF, except that, instead of having different people involved, we just have different algorithms that we're sort of the puppet masters for. So there are all these sort of informal CTFs, but it's such a part of our culture now that I think we often don't think back to the fact that this really came from somewhere. This came from a very formal structure that was designed to make rapid innovation. Inside the academic community, for those who are in sort of the academic community when it comes to machine learning, if you go to a conference and basically you see entire communities of researchers working on the same data sets, same tasks, same metrics, right? And they're shared. So it's really kind of neat. So I go to both statistics and machine learning conferences. In statistics conferences, you talk to them, you say, oh, what are you up to? And they'll say, I'm working on, time series or latent state models or something like that. And then as soon as they kind of drill down a little bit further, you have to say, oh, hold on, explain to me your domain a little bit more. Like, what's going on with your data? Does your data have this characteristics? All of a sudden you have to start asking a million questions to really understand what they're doing. On the other hand, you go to a machine learning conference, you say, oh, what are you working on? And it's like, I'm working on chatbots. Like, boom, you know exactly what they're doing, right? You know exactly what their data set is, you know exactly what their task is, you know exactly what their metrics are. You don't have to really be involved in this long like discussion of, well, what exactly are you trying to get at, and et cetera. You know exactly what they're doing. And so it's a really nice, it's kind of nice in a way, right? Because it's very low friction. There's not a whole lot of work involved in sort of getting people, you know, in sort of like trying to pick apart what different algorithms or different models are actually doing. We have a very easy way to compare them. So in our kind of relaxed CTF, oftentimes, you know, these aren't really heavily debated anymore. So you'll see whole communities sort of all of a sudden come like 10 years later after working on the same task, same data set, they'll say, wait a minute, maybe we got to change up our data set a little bit, or maybe we got to slightly change our metric. And they'll do so, and you know, that's you know, progress, but it's not really a heavily debated thing. They kind of come to this realization slowly. You know, data sets, I'm sure you've created your own training, validation, test split, you know, data set, these kind of splitting the data sets really left to the individual often in a relaxed CTF. Tasks don't really change as often. I think a lot of that's because our tasks are looking a lot more like deployment tasks, things that we actually want to use in deployment. And so our tasks are kind of more static in that sense. Code isn't as readily shared. Remember in the original CTF, the only way I could get you to, I could compete is if I sent you my code. Well, that's not necessarily the case anymore. We can kind of publish or write a blog post about code that we don't really share. Now, that's not true all over. Yeah, there's a lot of sharing of code, which is really nice, but it's not a mandatory as it was back in the original CTF. And just that overall kind of deliberateness has gone away from the CTF. Now, I'm just kind of bringing that up for more of a context of the history. I think it's a very interesting history that really hasn't been written down much. And I think I would really like to see a more formal study of the history of the CTF. I think it's a really interesting topic. But back to sort of where we are now in this kind of relaxed common task framework as a data scientist, and we're using it, what are sort of the benefits of operating in this relaxed CTF? Well, we don't have to worry about sampling. You know, we typically have either a convenience data set or a data set that's been handed to us from maybe the company or whatever it is, a task we're really working on. We're not worried about sampling issues there often. I mean, sometimes we are, but often we don't have to worry about that. There's no real worry about a data generating function. We kind of assume that our data is static, it's there. We don't have to worry about, like, we don't have to think too hard about like what's the mechanism that's generating this data? Am I trying to model that mechanism? It doesn't matter, right? We just take an algorithm, we apply it. If it's working, that's awesome. If it's not, we throw it away. What enables that, the ground truth is always available to us, right? How do we know if our algorithm is working? We can see, are we getting the right answer? Are we getting the right predictions? Are we getting the right classifications? So when we're kind of ramping up our algorithms, again, we're taking away the hard work of like, oh, is this mathematically justifiable? Is this tweak that I'm doing, how's it going to mess up my confidence bounds? Don't worry about it. We have the ground truth. We know if we're going to get the answer right, right? You just run it and see. And so it's very nice. It's very frictionless. It's very fast. And again, we have we know how to compare algorithms, right? We're not worried about what's the algorithm saying about this domain. We're just saying, are you getting the right answer or not based on our metric? And we can rank algorithms. This algorithm got the best, you know, it did the best on our data set. This algorithm did second best, et cetera. Okay, so it's very, very nice to work inside of this relaxed CTF. But here are the key ramifications for working inside the CTF that we should be aware of when we are selecting the best algorithm for our task, okay? Again, I'm gonna sound like a little bit of a broken record here, but these are important. So these are the ramifications. The ground truth is always observed. That's sort of like a little security blanket for us, right? We're deploying, we're sort of testing out this algorithm, and we don't have to, again, worry about technicalities. We just look to see if the algorithm's working. We always have that data that we can observe the ground truth. So it's a nice feature, but it's something that we have to be aware of. If our algorithm isn't working, we can adapt the algorithm in a reasonable time. Our data is actually static in the CTF that we set up, right? Our data is going to be there tomorrow. It's going to be the same data. We can go to bed, we can sleep on it, we can come up with some heuristic tweaks that we want, or maybe a different, think about a different algorithm we want to try it again tomorrow. There's no time crunch. We just lost maybe a day in trying a bad algorithm, but who cares at the end of the day, right? Our data is not going to change on us in a way that now we're going to have to somehow scramble to keep up with. We can tolerate error. Again, like we get it wrong, who cares? We go to bed, right? Let's say we're working on a cancer imaging data set and we try an algorithm out and it just really doesn't work, right? It really kind of fails on the test set. It's fine, no one needs to know, right? We just kind of go to bed. No one's, we've not sent this to a doctor. No one's, being harmed by the fact that our algorithm in our training of our algorithms in our little CTF that we're running has failed. It's not a big deal. So we can just kind of go to bed, try again tomorrow. So there's no real consequences, except again, the fact that maybe we lost a day, but that's about it. And because we're using outcome reasoning, because our judgment is, are we getting it right or not? We don't have to worry, at least in training up our algorithm or comparing algorithm, we don't have to really worry too much about like, is this algorithm doing what we think it's doing? Is this algorithm, conforming to our beliefs about the data or about our domain? It's kind of, that's a secondary concern that isn't, we don't have to necessarily, if we don't want to, we don't have to really worry too much about. Okay, so this is sort of the ramifications of us working in the system where we're essentially running bake-offs. And these ramifications, by the way, were derived from what we saw in the CTF and how the CTF worked. Okay, so this is the big idea here. When we're justifying an ML algorithm for deployment, we're actually really trying to justify the use of outcome reasoning. We're not necessarily justifying the use of that algorithm versus that algorithm. Why? Because that's justified by looking at which one's doing better. We're really trying to justify to our shareholders, or to our stakeholders rather, hey, this form of reasoning about algorithms is appropriate for the problem at hand. Okay, that's a departure from how we justify model reasoning. When we use model reasoning, where we're trying to map to the domain of interest, there we actually take our specific model and say, this is the model we want to use. Let's run it through all the experts we can to kind of get their okay and say, yes, this is used, this leverages what I know about my domain, but also doesn't make make decisions based on unknown parts, right? This model looks good to me. That's a very specific model. That's how we justify the use of that model. When it comes to outcome reasoning, though, we're justifying the form of reasoning. We're saying, can we use this sort of bake-off idea for our problem at hand? Okay, because again, the algorithm itself, in a way, doesn't matter, right? That's based on some technical aspects, but also based on the fact that this one's doing better than other algorithms, right? And again, there are things that I'm kind of sweeping under the rug a little bit here, but that forms a huge part of that decision. So this is when we want to loop in our stakeholders at this level of, should we even be using outcome reasoning? So we've derived from our study of the CTF and from our study of outcome reasoning, we've defined 4 key dimensions of discussion that we should engage with our stakeholders on, and our primary stakeholders in this case. And on the extreme, if each one of these 4 are fully satisfied, then we're essentially recreating our problem, our prediction problem that we're interested in, essentially recreates a little CTF. It mimics the CTF, which is ripe for outcome reasoning. So we can unleash all the power of our algorithms that we desire, right? It looks like the CTF, it acts like the CTF. Let's use these powerful algorithms developed in the CTF. On the other hand, if some dimensions aren't fully satisfied, then that's where sort of the interesting discussion occurs. But as you'll see, it can occur at the level of non-technical stakeholders, right? And we might decide that there are some trade-offs that we can make. We might, okay, well, let me just show you the 4 here. The first one is measurement. Can we measure at least a function of the outcomes? Do we actually get to see the outcome eventually, or can we measure some function of the outcomes? The second one is adaptability. You'll notice these are kind of mimicking those key sort of like ramifications of the CTF. Can we update our algorithm on a useful timescale? If we notice that we're starting to make bad predictions, can we update it in a useful timescale, or is that update going to actually take too long, or not be useful in terms of the sort of the flow, underlying dynamics of our data? Are we resilient to error? Do we have a high tolerance for accumulated errors? That's the third sort of dimension that we can discuss with our stakeholders. And the fourth is, do we have a high tolerance for disagreement with beliefs? So do we care that much that our algorithm is upholding the beliefs of our scientific domain or ethical concerns, things like that, or intuitions about the domain, things like that. Again, if we kind of satisfy all of these considerations, yeah, we can observe the outcomes. We can, if we see that we're getting predictions wrong, we can update on a useful timescale. We can tolerate getting predictions wrong for us to learn that our algorithm's sort of starting to fail. And also that we don't really necessarily care that we're making decisions for particular reasons, right? That our algorithm's just saying, yeah, this is the decision you want to make. That's if we kind of load highly on all of those four aspects, then we are ready to use outcome reasoning. If we don't, then we can make some trade-offs. For instance, one that we'll see in a minute is, let's say that we don't really measure all of the, we aren't able to measure all of the outcomes. We don't get to see all the outcomes for the entire space of our predictions that we're making, but we have a really high tolerance for errors. Then I say go for it, right? Like maybe we can try and measure, maybe outcomes are really expensive to measure, then maybe we measure a portion of the outcomes just to kind of make sure that our algorithm is more or less doing well. But again, we have that high tolerance for error, so we're not that concerned if we're making, some mistakes along the way. So there are ways to make trade-offs, and we'll see that in action in just a minute. So let me run through a few examples. So, and these are not meant to be fully worked out examples. These are just kind of meant to get you starting to think along these lines. So the first example, Amazon wants to sell products, product A or product B. It can show one ad at a time to one customer. So the question is, which ad should we show? We can observe if people buy product A or product B. So, I mean, we don't fully observe whether or not they would have bought the product if they had been shown a different ad, but we can use clever statistical methods to essentially get good measurements or a function of the measurement of our data there. So we do satisfy measurement. And again, like these are things that you should be discussing with your stakeholders. I'm kind of making all the decisions right here. So it's not a realistic scenario, but hopefully you can see how this discussion might go. We get tons of customers coming through. Amazon gets tons of customers coming through, and they're not like rapidly changing their purchasing habits. So an algorithm that works well today will probably work well tomorrow, probably work well next week, maybe not next year, but we've got time to adapt the algorithm. So yeah, we've got good adaptability on our algorithm. If we see we're starting to make some, not do so well with our ad placement, we can change it, and our changes will still be valid a month from now or a couple months from now. The ad placement is helpful, but people are still going to buy these products regardless. It's not like a company's going to go bankrupt because we kind of used a bad algorithm or our algorithm was making mistakes. So we're resilient to any kind of errors that we might accumulate. And then again, there's no real concerns about why we're showing ads. So we're pretty agnostic to why we're making these decisions. The second example, high frequency finance. We want to make rapid trades. Often one of the big things we want to estimate is an instantaneous covariance matrix of our assets. We certainly can't directly observe the covariance, but we can sort of approximate it if, are we making money using our algorithm? So I would say, yeah, we can have a function of the actual outcome of our data, how well we're doing. In high frequency finance, algorithms are expected to eventually fail because the market will adapt to whatever you're using. So we always have, again, I'm talking like I'm in high frequency finance, but they always have algorithms waiting in the wings to kind of come back and substitute. So very adaptable, not a problem. Winning and losing is all part of finance. It's a well-studied problem. They're very resilient to, having some losses, before they recognize that they need to sub in their algorithm. And no real ethical concerns, so they are agnostic to why their algorithm is making a decision. Now, the FTC might not be agnostic, so I don't want to like make it sound like this is all that they care about. But I'm kind of just again going through toy examples. So let's see what happens if we change our stakeholders. What might happen? So now we're going to think about family finance, and all of a sudden we have a family that we actually does care about how we're investing money. We do get to see if the algorithm is making money. So we have measurement, we do satisfy adaptability in that, like, losing a little bit, 1 week is not a horrible thing. We can adapt our algorithm. But we probably don't have the same error tolerance that we do with high frequency finance, right? We're dealing with someone's money. We're not dealing with like billions of kind of, one of my friends put it, monopoly money, essentially. So we are not as resilient as we are in high frequency trading. The biggest issue is that maybe the family doesn't want to make certain investments and wants to make sure that they stay way far away from like, guns, or that they have a certain opinion about the market and how it might evolve. And so, again, we're not necessarily agnostic here. We do care about why our algorithm, if we choose to use an algorithm, is making the decisions that it's making. So here's an example where we really kind of have to discuss with the stakeholders more to see where we fall along these lines. So the idea that I want to show with this example is just that changing the stakeholders does actually change sort of the way that we load onto these sort of facets. Another example would be elections. So it happens every 4 years here in the United States for presidential, say. But the underlying reasons why people vote change in those 4 years. And so any algorithm, if we were to wait to see if our algorithm were getting the predictions right, by the time we decided, hey, we need to change our algorithm, the voters have moved on, right? They've changed their reasons for their underlying why they're voting. And so we don't really have that adaptability. So that's an example where adaptability just fails. It's essentially a one-shot prediction when we vote in an election. The last example that I want to show is Twitter. So this is actually a real study, a really nice study. They were looking at, I don't think they were looking at tweets, I think they were looking at Facebook posts from Congress people about whether or not they write about a post about the Me Too movement. And this was maybe a couple of years ago. I think there was something like 47,000 Facebook posts that they wanted to analyze. They could have hand coded all of those posts, but it's costly, it's error prone. So they wanted to use an algorithm to do that. The issue, of course, is that what they did was they trained an algorithm on about 500 posts and then validated it on about 500. And then on the other 46,000, they ran the algorithm and kind of took those outputs as sort of the truth. The issue is that we'll never know, right? The whole point is to not have to go through by hand and validate the answer. So we actually don't know about 46,000 posts, whether or not we were getting them right or not. And so in reality, we kind of fail measurement there, right? There are 46,000 posts that we never get to validate. What's interesting here, though, is their conclusion was basically that, Democrats post more than Republicans, women post more than men about Me Too. That's pretty consistent with our sort of beliefs going into the study. And so, it's nice to have that kind of litmus test, but it didn't really change anything about our state. It didn't really have dramatic implications. So we're probably pretty resilient to errors. Let's say that it erroneously, I'm kind of making up that it was erroneous, but let's say it erroneously said that men posted more than women or Republicans posted more than Democrats. That would probably prompt just more study on the idea, like maybe some people going in and thinking qualitatively about what could have changed. Nothing's really of like dramatic significance is going to occur. Now, imagine the same study, though, but where there's going to be a shift of about $50 million of funding, right, in Congress. They're going to take the results of the study and shift about $50 million funding. Now, hopefully you're kind of starting to say, wait a minute, 46,000 Facebook posts that we don't actually validate, that's a lot to change $50 million in funding. So now, all of a sudden our resilience isn't as high. So we might want to say, okay, instead of only validating on 1,000, let's validate on 20,000 or so like that. I'd be more comfortable with that sort of a sample size. So you can see how the interplay of resilience and measurement could, and understanding those dimensions could help us in making a better study. I'm running out of time, so I want to get to my final thoughts here. Outcome reasoning, the big thing about outcome reasoning is our sort of validation of our algorithm happens after deployment. We deploy an algorithm and then we see if that algorithm is doing well in the real world, okay? Stakeholders have to be comfortable. What you wanna get is stakeholders in the position where you say, look, we're gonna be validating this algorithm after we've deployed. So they have to be comfortable with that. They have to be comfortable with the idea that it might accumulate errors. On the other hand, model reasoning occurs before deployment. We get all these, experts together. We talk about how this algorithm maps onto their domain. We are comfortable before we deploy with, okay, this is to the best of our ability. This algorithm sort of represents our current beliefs on the subject. Now, buy-in is vital, right? Because that when stakeholders buy into our use of a particular form of reasoning, then they are essentially owning the problem, right? They are saying, yes, I'm okay with this form of validation, this form of reasoning about our data. And so it's vital. I'll say one more thing, which is I don't want you to come away thinking, machine learning is not so great. It is amazing. If you can use machine learning, if you can do outcome reasoning on your problem, you should. It is a uniformly more powerful method of reasoning about your data than model-based reasoning. However, I would caution that there are, more limited situations in which it is the appropriate form of reasoning without maybe modifications to your problem, like for instance, a human in the loop, things like that. So it's really something that we would like to use, but we want to be careful about how we use it. And I'm hoping that the framework that I've put forth today will help you discuss with those non-technical stakeholders the pros and cons of using outcome reasoning for your problem of interest. So I'm going to end there. Thank you so much. This has been a lot of fun. I hope that you've come away with some thinking points, and I'm open for questions. And of course, you can always email me if you want to discuss further.
Awesome. Thank you, Jordan. I have a quick question. If folks we have probably just a couple minutes here. If folks do want to share questions, please put those in the chat. So this is really interesting. Are you seeing this used with stakeholders, or is this a framework that you are trying to actively get out there to have folks working on?
Yeah, so that's a great question. So we are still actively trying to get that out there. We've talked with several groups. For instance, we talked to the folks at RAND, which is a big sort of policy think tank, or I don't know what you want to call them, but they're incredibly excited about it. I think, a lot of times we talk to statisticians who share our reservations to a certain degree of should I use machine learning or not? It's a really powerful thing, but I don't know if I want to take the risks. And they when we talk to them, they recognize this is a really kind of a nice way to frame the discussion and sort of to think through the problem of, well, should I be using machine learning? Do I have a tolerance for these kind of potential errors? Am I willing to sort of wait and see how my algorithm does? I think they think it's a really nice framework for thinking through the problem, but also with talking with non-technical stakeholders, to convince them hey, here's why we might be a little more worried. Because, I don't know about you. I talk to people and they're so excited about AI and machine learning, which is awesome on one hand, but I'm also hold on, it might be great, but let's hold on. Let's think through this. And, this is one way to sort of present it to them, to say, here's the reality of the situation. And I'm happy to use it if it's the right tool, but, this is where we need to be thinking just in case it isn't.
Thanks. Yeah, seems really helpful. Awesome. All right. With that, 6 o'clock. So thank you so much for your time, Jordan. And thank you everyone for joining. Hope you all check out Data Week DC and keep attending events throughout the week. Have a good night.
Thank you.
Great talk, Jordan. Thank you.
Thanks. See ya.
We will post the recording on YouTube and link to it in the meetup.
Yep. Wonderful. Thanks. Bye.